All right, so going to talk about active filters real quick. Active filters are basically filters that are designed with active and passive components. Up to this point, we've been talking about passive filters, which are basically just designed using resistors, capacitors, and inductors and nothing else. Active filters throw transistors into the mix, which means we can use op amps. And not only can we get the response that we want, we can also add a factor that will allow us to not only pass signals at the frequencies that we want, but also amplify them, or basically gives us more degrees of freedom for shaping the frequency response that we want for our filter. Okay, and so before we can understand exactly what's going on with an active filter, we need to remember two things. Remember that for the RC circuit, we basically got, this was V in, this was V out, right? We basically got a response, V out over V in equals 1 over 1 plus j omega RC, right? That was our, I can never draw these omegas. There we go. We basically got that for our frequency response. And way back in EE 220, we got for an inverting op amp topology, let's just pull this way out here, or for the inverting topology, actually, we're gonna go ahead and ground this. And so this would be my V in, this would be V out. If I were to put a ground here, I could measure the V out there. This is my plus and my minus. This is R1, this is R2. V out over V in for this circuit, the inverting amplifier circuit. I might have been saying non-inverting this time. I meant inverting this entire time. V out over V in equals minus R2 over R1. Okay, so those are the two concepts that we need to keep in mind when we analyze this active filter that we're going to analyze here. Okay, so let's put boxes around those, one there and one here. And so this is an example of what an active filter looks like. Basically, we're going to have our source, AC input. We're going to have resistor here. And then I'm going to have an op amp just like this. Oops. Just like this. Where that's ground. And then up here I have my resistor, but I'm going to add a capacitor here as well. Okay, and so this is V out, this is V in. I'm interested in finding V out over V in, just like I have been this entire time. And I'm going to call this my series capacitor, RS. I'll call this my filter capacitor, or my series resistor, my filter resistor. And I'll call this my filter capacitor. And obviously, I hope you can see that these two impedances are in parallel. So I should be able to combine those into a single impedance. So if I were to redraw this circuit, I could redraw it like this, where this is an impedance. This is also an impedance. Ground, ground. And I can call this ZF, and I can call this ZS, where ZS is just going to be equal to RS, and ZF is going to be basically what I get if I have a resistor in parallel with a capacitor, right? It's going to be RF in parallel with CF. And if I carry out the math, I want to save time here, because I know this video is going to get long if I don't. But that is going to come out to be RF over, well, I guess I can just do it. It's basically RF times 1 over j omega CF over RF plus 1 over j omega CF. And of course, if I multiply top and bottom by j omega CF, I just get RF over 1 plus j omega RF CF, right? that's what I'm going to get for the impedance ZF. And so now if I analyze my inverting op-amp topology here, I know that the V out over V in should just be this impedance ZF, which in this case was R2, now it's ZF, minus ZF over ZS, right? So if I can pretty quickly just find V out over V in for this, which is the transfer function I'm interested in, right? This is V out. Minus R2, so in this case it's going to be minus ZF. It'll be minus RF over 1 plus j omega RF CF. And then that whole thing over ZS, which is just RS. And I can rewrite that as minus RF over RS multiplied by 1 over 1 plus j omega RF CF. And that is my transfer function for my active filter. Maybe you don't notice anything particularly interesting about it, but what you should notice is that the regular old low-pass filter that we had the response 1 over 1 plus j omega RC, and that pops up right here in my active filter, 1 over 1 plus j omega RC. It's just talking about RF and CF in this case. The difference now is that if we make RF and CF, or sorry, RF and RS equal to each other, then this cancels and we're just left with V out over V in. Obviously the negative sign is in here, but we can do things with op amps like make another inverting amplifier with a gain of -1 to negate that. But we have control over this ratio of resistors, right? We can make RS whatever we want. So we could actually make it to where instead of just passing the signals that we want, we can get a gain at the signal, at the frequencies that we're interested in passing as well. And that's powerful in all kinds of applications. So I'm just going to leave this video here. I just wanted to derive the low pass filter, the low pass active filter transfer function here, and show you how this term basically is the same term that we had in the basic passive RC low pass filter. But now we have an extra factor out here which allows us to control the gain of our filter. Okay, so I'm going to go ahead and end this video right here. And I think in the next video, I'm just comparing and contrasting active and passive filters.